Namaskaram. Today we are going to discuss metrics of a linear transformation. That means corresponding to every linear transformation, we can find a matrix. That means we can identify every linear transformation in terms of numbers. Okay, and this concept is very useful in language of machines. Okay, this is a result. Let T be a linear transformation from n-dimensional vector space V into m-dimensional vector space W, and let B is equal to V1, V2, etc. Vn be a basis for V, and C equal to W1, W2, etc. Wm be a basis for W, because we assume that W is a m-dimensional space. That's why this basis contains only m elements. Okay. Then the matrix of T with respect to B and C is defined by like this. The matrix of T with respect to B and C, because this matrix depends these two bases. Okay, that's why we noted like this: matrix of T with respect to B and C. Okay, is equal to, it's a matrix, it's a m by n matrix, and Q1 is nothing. Q1 is the first column of this matrix. Okay, similarly Q2 represents the second column of the matrix, etc. Qn is the nth column of the matrix. Then how to find Qi? Qi is nothing. Qi is equal to, uh, this is the coordinate of T of Vi with respect to C. Okay, this is nothing. This is the coordinate of T of Vi with respect to C. So actually, what is Q1? Okay, Q1 means you choose first base element, that is our V1, right? Then you take the image of this V1, that is T of V1, right? Now it is clear that this T of V1 is an element of W, right? And C is a basis for W. So we can express this T of V1 in terms of C. Okay, so it has a coordinate. Okay, so we express T of V1 in terms of basis C, that is some arbitrary constant, some not arbitrary, some constant into W1 plus etc., some other constant into W2, etc., some other constant into Wm. That will be D11, and the next one is D21, etc., Dm1. Then how to write the coordinate of T of V1 with respect to C? That is nothing. You simply take these scalars and make it a column. So the coordinate of T of V1 with respect to C is nothing. It is D11, D21, etc. Dm1. You got it? So this is nothing. This is the first column of this matrix. Similarly, you can find Q2. How to find Q2? You take V2. Okay, V2 is a base element. So here you take V2 and take the image. Then find the coordinate of this T of V2 with respect to C, similar to this one. Then that is a second column. Okay, so totally this matrix has n columns, right? Corresponding to every Vi, we have a column. So n column. Then how many elements in each column? And each column corresponding to the coordinate. And each coordinate contains only 1, 2, etc. m elements, right? So it has m rows and n columns. That's why this matrix is m by n. So if a linear transformation from n dimension to m dimension, then the matrix corresponding to this transformation is an m by n matrix, right? You can find this m by n matrix using this formula. And also we will see that this matrix, the matrix of T with respect to B and C, is equivalent to our transformation T. Okay, we will see the relation between this matrix and our transformation. Okay, that means we can determine the action of T completely by using this matrix. Okay. Okay, consider this problem. Find the matrix representation with respect to the standard basis B in R square and the standard basis C is equal to 1t t square in P square for the linear transformation T from R square to P square defined by T of AB is equal to 2at square plus A plus BT plus 3B. Okay, we have to find the matrix of T with respect to these two bases. So what is our B? Yes, that is the standard basis of R square. That means P is equal to some 1 0 and 0 1. Okay, so as per our notation, and this is our V1 and this is our V2, clear, and these are W1, W2 and W3. Okay, this is 2 dimension and this is 3 dimension. So we expect a 3 by 2 matrix, right, as an m by n matrix. So how to find the first column of this matrix? Yes, we choose V1, then we consider T of V1, then we consider matrix of T of V1 or coordinate of T of V1, with respect to C. And this is our first column. You got the procedure. So we choose V1, and what is T of V1? Yes, here A is 1 and B is 0. So this term become 2t square, and this become T, and this term is 0. Right. So what is T of 1, 0? So this is equal to 2t square plus t. And next we have to express this image in terms of basis elements. That means what is the coefficient of 1 in this vector? That is 0. So 0 into 1 plus what is the coefficient of t? That is 1. 1 into t plus what is the coefficient of last base element? That is 2. So 2 into t square. So this is the expression of this vector in terms of basis. Now we can easily find the coordinate or q1. What is q1 or the coordinate? Coordinate is t of v1 with respect to c. It is nothing. You simply pick the coefficients. So 0, 1, 2. So this is our first column of the matrix, this 3 by 2 matrix. Okay. Similarly, you can find the second one. Okay. Next we have to find t of v2, then its coordinate with respect to c. Okay. So what is t of v2? Okay. T of v2 is equal to t plus 3. So we can write this as in terms of base elements. That means 3 into 1 plus 1 into t plus 0 into t square. So what is our coordinate? Yes. So q2 is equal to coordinate of t of v2 with respect to c. That is nothing. 3, 1, 0. Okay. So what is our matrix? What is our matrix of t? Matrix of t means we have to find the matrix of t with respect to b and c. It is nothing. First you write q1. Q1 is 0, 1, 2. Then q2. Q2 is 3, 1, 0. So this is the matrix of transformation with respect to these two bases. Okay. It's clear that the matrix is different if you change the basis. Okay. But there is a strong relation between such bases. Such matrices. Okay, second problem. Find the matrix representation with respect to the basis. B is given 1, 1 and 1 minus 1. In okay, this T stands for transpose. So normally we treat elements in R square or in Rn as a column matrix. Okay, that's why we put a transpose. That's all. And the standard basis C is equal to 1t t square and p square. For the linear transformation T from R square to p square defined by T of AB equal to the same transformation. So the only difference is here we change the first basis, that's all. Remaining all things are same. Okay, then what is the change in the matrix, or what is the matrix of this transformation with respect to these two bases? Okay, here these are V1 and these are V2 and W1, W2, W3. Okay, so first you have to find T of V1, then find the coordinate. Similarly, you can find T of V2, then the coordinate. Okay, then you can write the matrix of the transformation. Then what is the coordinate of T of V1 with respect to C? Okay, so here T of V1 is equal to 2t square plus 2t plus 3. So what is the coordinate? This is 3 into 1 plus 2 into t plus 2 into t square. So coordinate is 3, 2, 2. Similarly, T of V2 is equal to 2t square. This time equals 0 minus 3. So you can write this as minus 3 times 1, right? Minus 3 times 1 plus 0 times t plus 2 times t square. So that's why its coordinate is minus 3, 0, 2. Now you can write the matrix. You just arrange their columns of the matrix. So the matrix of T with respect to B and C. B is different from previous one. So the matrix is 3, 2, 2 and minus 3, 0, 2. Okay. Okay. Now in previous case, we discussed the same transformation, but the matrix is different. So that means now we have two different matrices corresponding to the same transformation because we change the basis. But there is a strong relation between these two matrices. Okay, we will see that in our next session. Okay, then there is a natural question. What is the relation between this transformation and its matrices? Okay, the answer is given by our next formula. See this. Let T be a linear transformation from n-dimensional vector space to m-dimensional vector space W, and let B is a basis of first one and C is the basis of second one. Then this is the relation between this matrix and image. Okay, this means V is an arbitrary element from a vector space V, and V with respect to B means the coordinate of V with respect to B, and these are metrics of the transformation. Then you take the product, and this product is again a matrix. That is nothing, that is TV with respect to C. That means the coordinate of image with respect to C. You got it? That means, okay, suppose this is our vector space V, this is W, and B and C are the bases respectively. And a transformation means what? Transformation is a function. A function is completely described by its action on an arbitrary element. Okay, what is T of V? That's all. Okay, so we can find this T of V using this matrix. That is the essence of this result. Okay, how? First you take an arbitrary element V from capital V, then you find the matrix of V with respect to B. That is possible. The coordinate of V with respect to B. That is possible. And we know that this is an n-dimensional space. So this is nothing, is an n by 1 matrix. Clear? And we have the matrix of transformation, that is T into so next we consider the product of T into this matrix. Okay, next we consider first we find the coordinate of V with respect to B. Next we take the product of these two matrices. This is also possible because this matrix is m by n and this is n by 1. So this product is nothing, product is again m by 1 matrix, right? So this product gives a matrix, and this result says that this product is what? That is the coordinate of TV, the coordinate of this image with respect to the basis in W with respect to C. Clear? That is the result. So this result says that this result says that this product is equal to coordinate of image with respect to C. We know that this matrix is again an m by 1 matrix, right? Then how to reconstruct this TV once you know the coordinate? That is very easy, by taking the linear combination with the basis elements. Suppose this coordinate is something like d1, d2, etc., dm. Then how to create this TV, or how to generate this TV from this coordinate? Yes, we can reconstruct this TV using like d1, w1. W1 is the first base element, plus d2, w2, etc., plus dm, wm. So you can reconstruct this image TV using this coordinate. That is the definition of coordinate. Okay, so if you know the matrix of the transformation, that means we know the transformation. Clear? And in this so in this way we can convert every transformation in terms of numbers. Okay, consider this problem. Evaluate T of 1, 3 using both direct and indirect methods for linear transformation, the same linear transformation. We use B as this matrix, this basis, and C as like this. Okay, so first we have to find T of 1, 3 use a direct method because we know the transformation. So what is T of 1, 3? Yes, using this transformation we can find T of 1, 3 as 2t square plus 4t plus 9. Next we are going to find this T of 1, 3 using our matrix of the transformation. Okay, and what is the matrix of this transformation? We have already seen in problem number 2. Okay, from our previous problem it is clear that matrix of T with respect to B and C equal to 3, 2, 2 and minus 3, 0, 2. Okay, then what is our procedure? Okay, our procedure is like this. We take an element V. In this case our V is 1, 3, vector 1, 3. Then next we have to find the coordinate of V with respect to B. Okay, this is a matrix. Okay, then we consider the product of these two matrices, this matrix and this matrix. That gives the coordinate of T of V with respect to C. Then we can reconstruct our T of V using the linear combination with the base elements. That is our procedure. What is coordinate of V with respect to B? Okay, here our V is 1, 3. So its coordinate with respect to B is 2 minus 1. That means we can write 1, 3 as 2 times this first vector plus minus 1 times second one. That's the meaning. Okay. And next we consider the product of these two, this matrix into this matrix. What is that? Okay, so this is actually 3 minus 3, 2, 0, 2, 2 into our V with respect to B, that is 2 minus 1. Okay, sorry, this is 2 minus 1 and the product is 9, 4, 2. Now you can reconstruct TV. Now this matrix is 9, 4, 2. Then how to construct T of 1, 3? That is equal to the first one, 9. 9 into first base element. That is what? That is 1. Plus second coordinate, that is 4, into second base element, that is T, plus last coordinate, that is 2, into last base element, that is T square. That is 9 plus 4T plus 2T square. This is same as this image. Okay. So this is the idea. Okay. This is your homework. Thank you.